In maritime operations, a hazard is a physical threat. Risk is a mathematical measurement, the probability of an outcome deviating from what is expected. To engineer safety, we first divide that probability into two distinct categories of exposure. The first is pure risk, scenarios where the outcome is strictly negative, or at best results in no change. A mechanical failure resulting in a catastrophic fire is a pure risk. There is no potential upside to this event. It guarantees loss. This visualization contrasts that with the second category, speculative risks. Here, outcomes fluctuate. They carry the potential for both severe negative losses and positive gains. These encompass external variables that dictate profitability, such as shifting currency exchange rates, the unpredictability of global freight markets, and fluctuating bunker prices. A modern shipping enterprise faces thousands of these intersecting pure and speculative variables daily. Relying on historical seafaring intuition to manage this volume of financial and operational volatility is mathematically impossible. Historically, the maritime industry operated on a piecemeal, reactive methodology. Regulations were written in the aftermath of tragedies, waiting for an accident to dictate the next survival tactic. To dismantle that reactive tradition, the International Maritime Organization mandated a standardized, proactive regulatory framework. They introduced the Formal Safety Assessment Protocol. The assessment is a rational, systematic process. It forces operators to continually evaluate both the financial costs and the operational benefits of actively reducing specific dangers. By enforcing this structure, safety transitions from a standard compliance chore into an integrated, quantifiable business strategy. This circular flowchart outlines the five-step framework, beginning with hazard identification. This requires listing every relevant accident scenario with its potential causes and outcomes. The map begins internally. It isolates technical risks like propulsion failure, machinery breakdown, and structural fatigue. It then integrates the human element, tracking personnel risks like crew injury, alongside social risks such as piracy or stowaway incursions. Finally, it expands outward to capture external exposure. This includes legal variables across different global jurisdictions, financial bad debts, supply chain purchase risks, and commercial volatility. If management fails to comprehensively map all 7 of these hazard categories, the mathematical evaluation that follows will fail entirely. Identifying a hazard is only a qualitative exercise. Step 2, assessment of risks, requires a specific mathematical model to quantify them. This graph forms the foundation of that assessment, the risk matrix. The x-axis plots the severity of a consequence on a scale of 1 to 5, from negligible up to catastrophic. The y-axis plots the probability of that event occurring, scaling from rare up to certain. This creates a highly specific 25-cell grid. The upper right quadrant represents high severity and high probability. This is the not acceptable zone, dictating immediate, heavy intervention. Conversely, the lower left area is the acceptable zone. These risks are statistically low enough to be tolerated without additional action. Between them lies the critical middle threshold, categorized as ALARP, as low as reasonably practicable. Events in this yellow zone are tolerated, but mandate strict, continuous monitoring. We can plot any event to determine its priority. A major tsunami, for example, plots into the rare but catastrophic cell. A slip and fall on deck plots into the likely probability but marginal severity. This matrix serves as an objective triage tool. It strips away subjective fear and provides a clear hierarchy for allocating capital. Simply plotting a node is only the baseline. Steps 3 and 4 calculate risk control options against their cost-benefit assessment. Looking at the matrix, we begin with the worst-case scenario strategy. This plots the node assuming 0 safety barriers exist, isolating the raw potential of the hazard. Next is the current situation calculation. This strategy plots the exact dampening effect of the hardware and safety protocols already installed on the vessel, pulling the risk down toward the ALARP threshold. Finally, the future situation models projection. It estimates the mathematical drop in probability if the company purchases and implements entirely new safety barriers. Capital is finite. The assessment requires finding the exact intersection where the cost to implement a barrier is entirely justified by the reduction in risk. For the final step, decision-making, management handles residual ALARP risk in 3 ways. First, risk avoidance. abandoning the activity. Second, risk retention, bearing the hazard using internal financial buffers like cash reserves. Third, risk transfer, shifting liability via subcontracting or underwriter coverage. Every single identified hazard must definitively terminate in one of these three gates. Acknowledging a threat and then ignoring it is completely removed from the process. As this diagram reveals, strategic risk management is strictly cyclical. The final decision feeds directly back into step one. The system operates on a constant influx of new data. Periodic reviews do not just check compliance, they act as the starting point for inventing new control measures. The total elimination of danger at sea is an absolute impossibility. The ocean will always produce extreme variables. But by strictly applying the formal safety assessment, the maritime industry ensures those variables are calculated, properly financed, and highly survivable.